All right, on to our next unit, and it's going to be on waves and light, and we'll start off with the properties of a wave. So, a wave is a disturbance which transfers energy and momentum. And you may be saying, Mr. Gillum, light has no mass. How can it have momentum? Well, we'll get more into that when we hit the modern physics unit 2 units from now, but for now, just know that it carries momentum with it. We've got 2 types of waves that we can see. The first type are electromagnetic waves, and the other type are mechanical waves. With electromagnetic waves, they do not need a medium to travel. When you look at mechanical waves, and we'll come back and see how the reason they don't need them here, mechanical waves, they require a medium. So when I speak, I have to transfer energy through the medium of the air to make the sound travel. When the ocean has a wave, the water is the medium through which that energy and momentum is carried. Whereas with electromagnetic waves, they are the wave itself. It's the photons that are carrying the energy. And when we talk about electromagnetic waves, these are your transverse waves. They are always transverse when we're talking about electromagnetic. For some mechanical waves, they can be transverse. That could be like moving a slinky side to side or waves in the ocean. In this case, particles move perpendicular to the wave motion. So this wave keeps traveling this direction. All that happens is this particle moves up and down along that spot. We got a couple different terms here. Lambda right here represents a wavelength. It's from one point to another point. These points up here at the top being called crests. These spots down here at the bottom being called troughs. Okay, these points right along this central line where the wave's going to wobble through, these are called nodes. Whereas the peaks, both crests and troughs, are at antinodes. The distance from the resting point to the highest point the wave gets away from the resting point is called the amplitude, represented by a capital A. Cool beans? All right, now let's talk about longitudinal, also known as compressional waves. These are like sound. So when I talk, what I'm doing is I'm putting some energy into that air, and the air gets compressed as the energy travels through it. I've pushed a bunch of particles into each other. Those particles bounce into the next. So what happens is as the wave travels through the air, we get sections where the particles bunch up, and then sections where they spread out. These are our crests, quote unquote. And these are basically just where you have, I'm looking for the term here, just compression. Whereas over here, where they're more spread out, that's called rarefaction. Again, a wavelength is just from crest to crest, so compression to compression, or trough to trough, rarefaction to rarefaction. And in this case, the waves are traveling in the same direction the particles. So the particles move back and forth like this. The wave moves back and forth like this. So they move parallel to wave motion. Now, the rate at which waves come to you is called frequency. Frequency is just like if I were to stand here and I got hit by 5 waves per second, that'd be my frequency. It's measured in a unit called hertz. That's just 1 over seconds. Whereas period is how long it takes for each wave to hit me. So take a second, think about this. If I have a frequency of 5 hertz, how long would it take for 1 wave to get to me? This tells me 5 waves per second, so each wave only takes 1/5 of a second, so 0.2 seconds. Now, I want you to leave a blank section here in your notes because we're going to do an investigation on this. How are velocity of a wave and amplitude of a wave related? So make sure when you come to class that you bring a cell phone, or at least have someone in your group with a cell phone that has a good slow-mo feature. Makes your life a lot easier. Continuing into the properties for waves, here we see, this is your standard physics equation, velocity is distance over time. But what is distance for a wave? Well, for our waves, it's going to be wavelength, and the time of a wave is going to be our period, which is capital T. Well, we know that this is just 1 over frequency, so what we can do is put it up here, and this is your standard wave equation right here. Velocity is frequency times wavelength. Now, specifically for electromagnetic radiation, V is always going to be the speed of light, which is 3 × 10⁸ meters per second, right around there. Now let's look how things are a little different for a fixed point on a rope over time versus a whole rope at a specific point in time. So this first one is the location of a rope at a fixed point in time. So this is like where all the sections of a rope are. You'll notice X is on our x-axis this time. So this measurement right here between two peaks, that is going to be your wavelength because that's the physical distance on the rope between two waves. Now down here, we have a fixed location on a rope over time. So imagine my arm's the rope. I'm just this one point on my arm, watching it go up and down over time. So now our x-axis has time on it, which means we're no longer measuring how far apart the wave peaks are. We're measuring how far apart they are in time. That would then become our period. If we were to take just one section of time and count how many waves there are in there, if that time was 1 second, that would give us our frequency. But notice how similar they look. It's almost impossible to tell the difference between these two graphs because they're going to end up just, the most off they can be is just slid offset right or left. They will still look identical in their separation as long as your scales are the same. Now here's a little practice one for you guys. I've got a wave up here, and I want you to tell me what it would look like if I were to take the wave and delay its start by 2 seconds in time. So here's my x-axis. This is 1 point on the wave, and I want to see what it would look like if I were to take the wave and shift it by 2 seconds in time. So go ahead and try it out, see what you can do with it, and then we'll come back together and go over it. All right, let's see if you got something here. So in this case, what I'm going to do is I'm just going to take this point and I'm going to shift it 2 seconds over. Well, that means I'm going down here, which means I'd be coming up over here. And what do you know? It literally is just offset. Looks like a DNA molecule almost. Isn't that crazy? The only thing that would change for this, if I were to make it a sound wave, is just going to be a measurement of compression. So if we did instead of displacement, we did density of particles, it would look almost identical here. Let's talk about another property of waves. So we've looked at one wave and what can happen to it as it changes through time. But now let's look what happens when we have two waves that come together. There's a principle called superposition. Remember, waves are just energy and momentum. Energy is a scalar. Momentum is a scalar vector because it can be directed. But two can overlap in the same point. So the same thing's true of waves. That energy will still continue going on. And when they're in the same place at the same time, you just add them up. So in this first case, we've got destructive superposition. In this case, wave above horizontal and a wave below horizontal. When they come in, they're going to combine. And since they're the same size, they'll just cancel right out. That's this purple section here. Then when the waves go past each other, the red continues below horizontal, the blue continues above. They pass like ships in the night. They didn't even notice. Constructive is just the opposite. If they're both in the same direction, then they're just going to add up. So in this case, I've got two. As they pass through each other, they add up together. And then once they're done, they just pass on through each other, and they don't even get changed whatsoever. So now we're going to try out some problems where I give you guys examples, and you see if you can answer them on your own. All right, I got two different situations here, each one with two waves traveling towards each other. What I would like you guys to do is predict the waves when their centers are on top of each other, what that waveform is going to look like, and then do one after the waves interact with each other. So go ahead, give it a shot. We'll come back together and see if you guys got what I got. All right, let's see how you did. So in this case, I end up with them adding on top of each other. This guy right here, the height of this maximum wave should be the height of this plus that. The waves just interact and add up. So anywhere there's positive, they add the positives together. Once they're done interacting, the waves are just going to keep going on their merry way, just like they would be if there was no other wave there in the first place. In this case here, this one's about twice as high as this one. So what I end up with is a wave that's just a little bit bigger than that one. It's about half the original size of this one. Same size as this one, just flipped over. Then when they're done, they go on their merry way. And that is all we have for wave properties.